So we'll now be discussing belt friction. So for this, let's consider a fixed surface S. Let me draw that. So this is the fixed surface S, and by this sign I am showing it to be fixed. Now I am considering a belt over it, which let me show a different color. From something like this. This is point A, this is point B. So you have a flat belt of mass lambda kilograms per meter, which is moving at a speed v on a fixed surface S. Okay. Now this belt makes a contact over the curve C. So this is the curve C. Okay. And A and B are its two edges which are in contact. So A is the slack end, or so called slack side, okay, and B is the end of contact. So an easier way to see this is a three-dimensional contact between a belt and a surface. Okay, so that it's not actually easier, it is harder, but it is easier to see all this if you see that there is no plane actually anywhere. Okay, so the curve C need not be a plane, not be a plane curve. Okay, so tension at say you can say that the tension at so T1 is the tension at the tight end B, and T2 is the tension at the slack end or slack side A. Okay, so we will be using path coordinates over here, which is measured from A. So S will be measured from A. Okay, and TSB the tension clearly, rho SB is the radius of curvature at any given S. Coefficients of friction will be mu K and mu S for kinetic and static. Okay, so at location S, let the normal and frictional forces be P Newton per meter and mu Kp Newton per meter. If it's sliding, then this is the frictional force which you can clearly assume. So in engineering applications, the weight is negligible compared to the tension. Obviously in belts. So this is S, say over here, measured from A, and one small segment of this can be delta S. So I'll show this delta S separately. Okay, this is delta S of the cable. Now let's first start with the tensions. So you have this as the, so this is the positive sign because this is the direction of the trajectory, this direction. This is the direction of the path. Okay, so that's why this will be taken as positive. And so the tension over here, so this was clearly the position S, and this will be S plus delta S. So over here the tension would be TET hat at S plus delta S. Over here it would be minus of TET hat at S. Okay. Now we want to indicate the frictional forces as well. So that is taken somewhere over here as mu k minus of mu k p et hat as the average into delta S. So we are taking basically the frictional forces acting over this. Okay, so that's why we are taking an average value, and that's why we are showing it acting at this particular point, unlike the tension which we are showing to act exactly at the end. Okay, so that's the first part. And the normal force we haven't actually shown, so that will again be shown as an average. Sorry. Okay, so this value would be shown as, okay, so this value is P e to the power of n. Okay, and this average into delta S. So this is what you have. Now we have to also mention what En is. En, capital N, okay, is the outward normal to surface S. Okay, is the outward normal to surface S at S, which is this point in the path coordinate. Okay, or the path coordinate. Now if you want to write the equation of motion, there is also one more term, okay, which we will perhaps write after this. So over here I will show this by a En, just to point out this coordinate system, En and Et. Okay, and this capital En is another one which is, okay, as we have already discussed on the surface. So now we have to write the equation of motion for this element in the path coordinate system. So let's first write the forces in the tangential direction. They are TET hat of S plus delta S minus TET hat S plus P. Now we consider the forces in the capital N direction, so that would be PEN hat average delta S minus mu K PET average delta S. Okay, now all of these written as a resultant of this, there will be a centripetal term or whatever else you would want to call it. Okay, this is in the radial direction, so this also is taken average. So every time you see average, it means it has been calculated over the entire small element delta s. Okay, fine. So this is there. Now one can divide both sides of this equation by delta s. Okay, so divide, sorry, why is it coming like this? Okay, divide both sides by delta s and then take the limit as delta s tends to 0. So you should clearly notice what will happen to this one. Okay, so this will become d by, or let me just do that anyways, let me just do that. Okay. So we'll have t et hat at s plus delta s minus t et hat at s divided by delta s plus p e n hat average minus mu k p e t hat average is equal to lambda into v square by rho e n hat. Okay, and this is average. Okay, now this particular quantity can be written as dt by ds, right? If the limit is taken as delta s tending to 0, this is what we can write this term. Okay, and it will obviously be in the et direction, plus one can have t by rho e n hat plus p e n hat minus mu k p e t hat is equal to lambda v square by rho e n hat. Okay, now one of the underlying assumptions over here is that we have written det hat by ds is equal to en by rho. Okay, so once you write this term as these two terms, you should, and this comes from, if you remember, equation 1.22. so please go back and check this. Okay, and you should be able to write this over here. So think of it like a chain rule of differentiation. Okay, okay, once this is done, you can write that in the you can separate out now the parts in the, on the other thing, oh sorry, which you should also note over here, that E small n is actually minus of E n capital N. Okay, just by looking at these two directions, you can say that E small n is the negative of E capital N. Okay, once that is done, please look at these equations in the n direction now. So E n, if you just look, okay, you will have you will have dt by d sorry, not dt, you will have t by rho sorry, why is this coming in? So let me just convert everything to the small en hat. So this would mean that dt by ds et hat plus t by rho en hat minus p en hat minus mu k p et hat equal to lambda v square by rho en hat. Now if you take the en directions separately, you should have t by rho minus p is equal to lambda v square by rho. This implies that p is equal to t minus lambda v square by rho. Okay. Et hat should be dt by ds minus mu kp is equal to 0, or you can just write it as equal to this. Okay, and mu k, and then p you can take from over here, that would be t minus lambda v square by rho. Now this implies, in the sense, if you use this and this, perform an integration, that would be looking like dt by t minus lambda v square equal to mu k by rho into ds t2 by t 0 to s. Okay, this integration if performed, so T2, remember, was the tension at the slack end, so this was at A, okay, and this is at any point S. That's why you have this 0 over here, because you are measuring S from A, and S is any point coordinate. So this would imply that you have t minus lambda v square by t2 minus lambda v square equal to exponential 0 to s mu k by rho ds. Okay, if we can rewrite this in terms of p, remember, is t minus lambda v square by rho, so we will just replace p over here, then p would become equal to t2 minus lambda v square by rho, and then this exponential term 0 to s mu k by rho ds. This is equation 2.73. Okay, now let me just draw this belt again, going from A, so this is, say, A, this point is B. Okay, so the curve, let me draw in a green color, is the curve going from A to B. This is the belt in green color going from A to B. So at any point, say S over here, we have this as delta S. You have as delta psi. So D is the point on the surface, okay, B is the point of belt. Yes, of course they coincide at this moment because the belt is on the surface, but I just want you to separately understand. So D is point on surface and B is point on they are coincident points. So along the tangent, if you draw at A, okay, and draw another tangent at B, say call this angle as theta, this angle will be theta, this is 90 degrees and clearly this is also 90 degrees. I'm not showing the tangent at S, this angle will be also psi, and similarly the angle formed by delta S will be delta psi. Rho is the radius of curvature. Okay. Now the speed of this at A is v, okay, and the speed of this at B is also v in this direction. Again, it's tangential at both the times. Now if you see this plane curve, the green color curve C, which is shown in green, the contact is over an arc AB. So the belt changes direction by theta. Okay, so right now it was going like this and finally it has gone like this. So this angle is theta. So that's why they say that the belt changes its direction by theta. And also ds by rho is equal to d psi. Okay, so just by looking at this triangle, you can say that ds is equal to rho into d psi. Obviously delta s tends to 0 in this case. Then this equation 2.73, which is written in front of you, okay, this should reduce to a value. Let's see what that should be. Okay, so what you have to do is you have to just substitute d psi, ds by rho is equal to d psi. Okay, so let's substitute this ds by rho equal to d psi in this equation 2.73. Okay, so ds by rho is over here. I hope you can see that. That makes this as t minus lambda v square by this equation t2 minus lambda v square is equal to e to the power of mu k into psi. Okay, because integral of ds by rho from 0 to s, okay, will be equal to psi. Now the next case again would be p is equal to this equation would be written as t2 minus lambda v square by rho e to the power of mu k into psi. Okay, and then t1 minus lambda v square by t2 minus lambda v square will become equal to e to the power of mu k theta. Okay, because then you want this psi to go from 0 to theta, or from a to b, or from 0 to s, and s is like s of b, so all of them mean the exact same thing. So you have replaced t by t1 over here. Obviously the angles psi and theta are in radians, so T max, as you know already, equal to T1 occurs at B, How do we know? I mean, just look at any equation, say like this one, okay, and it will tell you that t will become maximum when this exponential term will become maximum, and you know the graph of exponential e to the power of x, okay. So that's how you can do it, or you can just take a derivative and double derivative, whichever way it works. But you should know that the maximum value will occur at psi is equal to theta. Okay, so t equal to t1 occurs at b, and this is in the direction of VBD. Now to understand VBD, please look at this diagram. This is the velocity of B relative to point D. So B is a point on the belt, D is a point on the surface. Okay. So clearly the tension will act in the direction of VBD. Okay. Now if the velocity of D is a 0, then there is no problem, right? So you will just have velocity of B then. So this is considering the case where the relative velocity is considered. Okay. Now if you have a, say, a rotating pulley, okay, so belt is on it, then you can have for impending slip T1 minus lambda v square by T2 minus lambda v square is equal to E mu s theta. Okay, you can see why I have replaced mu k by mu s, and clearly for no slip condition this will be T1 minus lambda v square by T2 minus lambda v square by e to the power of mu s theta. So here I have replaced T by the maximum tension, which is T1, and clearly this is the case for slipping, so I have not written that separately. So for slipping, for impending slip, and for no slip, all the three conditions are written. So this is 2.75. okay, sorry, this is also 2.74. okay, now if for some reason the belt has a very low mass, okay, so if you have, say, inertia of the belt is ignored, please recall the primitive of mass inertia, okay, then lambda will be equal to 0. So then all these equations like 2.74 and 2.75, what will they become? For slip, this one, it will be T1 by T2 is equal to e to the power of mu k theta. For impending slip, you will have T1 by T2 is equal to e to the power of mu s theta, and for slip you would have T1 by T2 is smaller than e to the power of mu s theta. So this is 2.76. okay, now that makes it quite easy, and very often we try to use these formulas in the problems and applications which we see around us. It may also happen that the velocity is 0, or the speed is 0, meaning the belt itself is constant, okay, and then perhaps there is a rotating drum brake. So for a stationary belt, that means a stationary belt on a drum brake, So please look at what a drum brake is if you do not know, okay, and only then move ahead. In this case, the speed will be equal to 0, okay, and the conditions will be the same as this one, because either you make lambda is equal to 0 or v equal to 0, these terms become 0. So same conditions as above. So if you have, say, a spatial curve of contact, so until now you had a line of contact, right? It was the curve C over here was actually a line, even though it could have been a three-dimensional line, but it was still a line contact, this curve C over here. Now if this is not actually a line but a spatial if it's not actually lying on this plane, but but over this area, so you have to use this spatial replacement. So let me just show you one of them. So this T1 by T2 over here, okay, e to the power of mu k theta, this must now be replaced by T1 by T2 exponential 0 to s mu k ds by rho, okay. So you had already made this assumption over here, if you remember. Where did it go? Okay, this one. So this was for planar. So the curve C, I'm sorry, I was correct myself, was always spatial, but this particular assumption, if you notice, was making all this in a plane, and that's why ds by rho could have been substituted as d psi. But if it can't be, then you can just continue writing it like this, okay, as it was, without making that simplification. Okay, or this would then become T1 by T2 is equal to e to the power of exponential 0 to s mu s ds by rho. So this was for slip, this was for impending slip, and for no slip, have T1 by T2 is equal to exponential of 0 to s mu s ds by rho. Okay. Now let's consider a so-called V belt. So the way it looks like is this. So let me first draw what the belt is. This is the whole belt, okay, and this angle is alpha. So separately just draw this green part only, okay, this part only. This is the belt. So it's a V belt, and it's called a V belt because of the V shape, I am assuming. Okay, V belt in a V shaped groove cut in a pulley. So you have this semi-vertex angle as Okay, So the center line of the groove forms a curve C. The center line of the groove forms a curve C. So let P1 be the force normal to the belt. Let me draw that all over here. So if P1 is the force per unit length clearly, which is normal to the belt, I'll show this over here as P1. Okay, show this over here as okay. This is the normal direction, this is the binormal direction, and inside is the ET tangent. So this cross sign shows it's inside the plane at this point. So anyways it is perpendicular to EN and EB, but it's inside. So ET is equal to EN cross EB, if you remember. EN cross EB. Okay. Now the friction force, I mean if it is rotating like this for example, then the friction force will be coming out of the screen. Okay, that would be mu k p1 delta s, mu k p1 delta s, because it has to oppose the relative motion. The angle is alpha. Okay. Now if you want to write the equation of motion, or let me just call this as the distributed force on this. Force Q on the belt. So Q will be P1 into, so let's write first the P1 into two components, into En and Eb. So this would be minus of sine alpha En hat plus cos alpha Ep hat. Okay, then take the other P1. P1 is equal to minus sine alpha En hat minus cos alpha Ep, cos alpha Ep hat. Sorry, Ep hat. Ep hat. Okay, and then you have the friction also. I should not remove this. You have friction on both sides, so I'm just writing at 2 mu, okay, for each one of them, k p1 into Et. Okay. So this is the distributed force, okay, distributed over delta s. Okay, so that's why the units are matching, I mean, okay, so this is automatically by definition divided by delta s. Okay, so that's why we are writing it without the delta. The actual force would be, each term has to be multiplied by a delta s, so we are not doing that. Okay, now if you look at this one, the force in the minus En and Et direction, okay, so let's write the force in the minus En direction. P1, sorry, 2P1 sine alpha En hat minus, okay, and then in the ET direction, sorry, I'll just write it one more step over here. This must be equal to minus of 2 mu k P1 ET hat, okay, minus 2 P1 sine alpha En hat, because this EB terms will get cancelled. Okay, so that is why we can say that the forces in minus En hat and Et hat direction are P is equal to 2P1 sine alpha and 2 mu k P1 is equal to mu k by sine alpha into P. Okay, and why is minus En and minus Et direction important? Come back over here. Minus En is the normal direction and minus Et is the so-called tangential or the frictional direction. So this is what we have for a V belt. Okay, and if you compare this, so compare that with the flat belt. So this is instead of a flat belt, mu kp of a flat belt. So there is this factor of sine alpha which is dividing this. Now again for slip, so look at this one. This one, okay, so everywhere you see a mu k theta, you have to divide this mu k by sine alpha, okay, and all mu s by sine alpha and mu s by sine alpha, so on all these places for this particular V belt. So T1 by T2 is equal to E mu k by sine alpha into theta. This is for slip, okay. For impending slip, T1 by T2 is equal to e to the power of mu s by sine alpha into theta, and for no slip, T1 by T2 is smaller than e to the power of mu s theta, mu s by sine alpha divided to theta. Okay, so a statement which you should actually practically verify meaning you should visualize that V belt is better in power transmission than a flat belt, since the mu effective in this case is mu k by sine alpha. This is always greater than mu k. So this is for the flat belt and this is for the V. So since the friction is more, the power transmission is greater. Okay, So this is something which you should be able to see and understand, and how belts are used, and this is somewhat of a homework for you. Okay. Okay, so if you have, say, a circular pulley, okay, and then you have a belt which somewhat, say, wraps it like this. Okay. So say something like this. Okay, and this angle is theta. Clearly this angle is also theta. This will be T1 velocity v and T2 velocity v. So the angle theta is the angle of lap of the belt on pulley. Now let's see how power transmission happens. We have already seen a statement, but by this time you should have known. So in power transmission, there is a driving wheel or a pulley, and then there is a driven wheel or a pulley. So let me draw both. Okay. The belt, let me put in green. Okay. So this is the driver, and this is the driven. Okay. This has, say, the lap angle of theta 1. This has the lap angle of theta 2. Okay. So in this particular example, theta 2 is greater than pi and theta 1 is smaller than pi. Okay. Let's call it T. Sorry. Let's call this point as D, this point as A, this point as C, and this point as B. Okay. This has omega 1, this has omega 2, and 2 m1. Okay, so this is an example of a power transmission. So a driving wheel driver transmits power to the driven. Okay, so in this case, if mu s is the or same for both pulleys, okay, then the smaller angle of lap, which is theta 1 in this case, okay, is used Used where? Used here. Okay, these equations. Now on the driving pulley, okay, this one, let me draw the free body diagram again for this one. Okay, so you have, say, I'll just show it like this. TC, this is B, T, B. You have a reaction force R1, you have a reaction force R2, just because there is a constraint over this, and then the resultant of this can be R. M1 and omega 1. So in the driving pulley, input torque, so this is the input M1, okay, perhaps through a engine, okay, or a human, for example, applying this input torque M1. This is in the same direction as omega 1, same direction as omega 1. I mean, this is something which you can like for a chakki, okay, which is used for I mean, you get the atta out of it, so that you can visualize. So you apply the moment and then the omega is in the same direction. However, for the driven pulley, okay, the load, sorry, the load or so-called output torque, let me just put that over here. M2 is the opposite direction of omega 2. Okay, now if you have a uniform rotation, meaning for driver, okay, meaning omega 1 is not changing. I hope you can see the diagram. Okay, for driver, then MOZ is equal to M1 plus TC minus TB into R is equal to, sorry, R was not the resultant, it was the radius. Perhaps we should have separate symbols for this. Okay, R is the radius of this. So MOZ would be equal to M1 plus TC minus TB into R, just because we do not want any resultant moment, okay, because if it would be, then it would start to accelerate. That's why we are considering case of uniform rotation. So this would mean that TB minus TC is greater than 0, or TB is greater than TC. Okay, this is something which you can verify. Look at the direction of M1, R is a positive number, so what possibility do you have? Okay, okay. So in this one, you have a maximum tension in over here in this segment, and you will have the minimum tension over here. Maximum pressure on the pulleys is at B, and the minimum is clearly at C. Okay, okay, so and for that, I mean, you have to just look at this expression. So I will just write it somewhere, that say using 2.76. I will write this so that you can verify that. Using equation 2.76, verify first that the belt tension is maximum in segment AB and minimum in segment CD. Okay, so if T naught is the allowable tension, so obviously you want to compare it with the maximum tension, and that happens in the segment AB. Okay, T naught is allowable tension, maximum allowable tension in belt. Okay, so you want to take the case of, say, impending slip. T1 minus lambda v square by T2 minus lambda v square. So this is equation 2.75 equal to e to the power of mu s theta. Now you want to say that the power transmitted would be T1v minus T2v. T1 minus mu s theta. Now if you want P to be maximum, we have to have Tp by Tv is equal to 0 and a double derivative test. Because a single derivative can also give you minima. Okay, so this will give you T1 is equal to T naught, or sorry, 3 lambda v square equal to T naught. So the maximum power is transmitted when v square is equal to T naught by okay. So we now want to discuss the frictional torque at a thrust bearing and frictional clutches. So for this, let's take a generic case first, and then we'll see how this can be seen in terms of a bearing or a clutch. So I assume at this time you already know how a clutch works in an automobile. If you do not, please pause the video right away, understand exactly how a clutch works, what a clutch plate is, okay, and what's the purpose of a clutch in an automobile. Okay, so bearing is something you should already be knowing by this time, so I'm not too worried about that. Okay, let's first take a simple case like this. So if you have an axis symmetric body, one in contact with axis symmetric body 2. Okay, now by axis symmetric it can be either conical or flat or spherical. Okay, the idea is that it should only depend on the r distance, radial distance, not on the angle theta. Okay, so these are the two bodies in contact. Now understand what P and M shown over here exactly means. The axial torque M needed for impending axial rotation of body 1 under an axial thrust P is to be determined. So you have to essentially find the relation between this M and P. What is M? It's the axial torque M needed for impending axial rotation. Clearly there will be friction acting of body 1 under an axial thrust P is to be determined. Okay, so you have to find a relation between M and P. Let's now try to draw a free body diagram of body 1. So now we can go something like this. We have P, we have M, this is the axial. Okay, say at a distance r is the radius over here, so clearly this will be r plus dr. Okay, this distance is ds. Okay, so you have to now consider an elementary ring of the contact surface with width ds and radius r. So the normal makes an angle of 90 minus alpha with this. So let's call this as in the middle, let's put that as P. Obviously this is per unit area, so it is P is in per meter square. Okay, so this makes an angle of 90 minus alpha with the axis, with this axis. Okay, so if with this axis, if it makes 90 minus alpha, that means this angle is 90 minus alpha. Okay, okay, that's the first part. Frictional force over here should be outside. Okay, so pointing out of the screen, that should be mu s p. So this direction, though I am calling it outside of the screen, but that's just because of this position which I have drawn. Okay, in reality this is a circumferential direction. Okay, so this is the most generic word, circumferential direction. Okay, now in this case, if you want to write the equations of equilibrium, then the force P has to be equal to integral over this small element. This would be what, P sine alpha into 2 pi r, okay, into ds. So the area would be 2 pi r into ds. and the moment m would be equal to the frictional part, so that would be, let's say, the r into mu s p, okay, 2 pi r into ds. This implies that m by p is equal to mu s r square p ds. S r p sine alpha ds. So this is the generic case. Now this shape which you are seeing over here will be specific now. So let's start with the conical bearing. So in this case you have something like this, and clearly this is in dashed part is showing the body too. Okay, this is the axis P M, this radius is R1, a generic radius is R, okay, this is R plus dr, this is again ds as before. P acts like this angle is alpha, okay, and mu sp acts in the circumferential direction, okay. Now in this case, for a conical bearing, clearly alpha is constant. In the earlier case, alpha would change depending on where you are, okay. In a conical bearing, that's not the case, and ds equal to dr by sine alpha can be written, because you can make this triangle over here as ds, this somewhere over here, and so this is a line which you draw, so this is a ds, okay, and this distance will be dr, okay, and this is clearly alpha, so sine alpha will be equal to dr by ds, okay. Now once you make these substitutions, the m by p, okay, m by p meaning the actual torque needed for impending a rotation of body 1 under this thrust, would be equal to integral r1 to r2 mu s, because it's impending rotation, dr by sine alpha into r1 by r2 rp dr. This is equation 2, okay. Now in say 1 dot or case 1, let me just say, so if you have a uniform P, that would mean that m by p in this case, so p would automatically come out, okay, and the numerator and denominator, it would get cancelled, so your final answer will clearly not depend on p, and this would just be if you integrate 2 mu s by 3 sine alpha r2 cube minus r1 cube by r2 square minus r1 square. This is equation 3. And similarly case 2, if you have case 2 is a case where P is equal to C by R. I will tell what it is immediately, but what you do is just substitute P equal to C by R over here and over here and over here. Okay, this would make this as M by P is equal to mu S by sine alpha R1 plus R2 by 2. Okay, this is equation 4. Now this case of P equal to C by R is actually called uniform where. Okay, and I'll explain this now why this is called a uniform where. So the amount of wear at radius r in n revolutions is proportional to the distance 2 pi r n through which slip takes place. Slip takes place and intensity of friction. That would be mu s into P. So if the wear, so the wear is a combination of both of them, and hence the total wear, the wear due to both of them can be written as is proportional to 2 pi r n mu sp. Okay, both of them. For uniform wear, you can say, or for example wear then will be equal to z, some constant, 2 pi r n mu sp. Now for uniform wear, this z into 2 pi r n mu sp is constant. Okay, this implies that rp is equal to constant is equal to c. Okay, let's call it, because 2 and pi and n and mu s are all sort of constants. Okay, so this is why you can say that P equal to C by R is a case of uniform wear. Okay, by uniform we mean that it will the dependence of this pressure P, okay, the normal P with R. Okay, so for any given number of rotations, any given friction coefficient, P will be inversely proportional to R for uniform wear. Okay, so let's call this case as M1 uniform P, and for uniform wear let it be called M2. Okay, so I'll write it as M1 by P. This is for uniform P. It is equal to 2 mu s by 3 sine alpha r2 cube minus r1 cube r2 square minus r1 square. Okay, and m2 by p, this is for the case of uniform wear, this is equal to mu s by sine alpha r1 plus r2 by 2. So m1 minus m2 will be mu sp by r1 minus r2 whole square, 6 into r1 plus r2 sine alpha. Okay, so this is something which you should be able to verify, and this quantity will be greater than 0. Why? Because mu s is greater than 0, 6 is greater than 0, p is greater than 0. Okay, r1 minus r2 whole square will be greater than 0, and r1 plus r2 will be greater than 0 because it's a summation of two radius r1 and r2. Okay, so r2, I mean, maybe I forgot to tell, but it's the final radius. This is r2. Okay, r1 is the initial radius, r2 is the final radius. Okay, so this is greater than 0, and this automatically implies that m1 is greater than m2. Okay, this means the resisting moment due to friction decreases when the bearing is worn out. Okay, for m2 it is lesser, m2 is lesser. Okay, so the resisting moment due to friction decreases when the bearing is worn out, and hence every time you service your bicycle, okay, if the bearings are worn out, they replace it, because the resisting moment or its ability to sort of transmit power, etc., reduces. So you should keep this in mind and think of examples, find out physical examples. Okay, now the next case can be, say, a flat bearing. So you have, say, okay, R1, R2, so this is P, inside the screen is mu SP. Okay, so for a flat bearing you have alpha is equal to pi by 2, and in this case you would have, say, m by p is equal to r1 by r2, this equation. Sorry, this equation. Okay, this equation we want to write. Okay, so that should become mu s r square p dr r1 r2 rp dr. Okay, so and m by p would be again 2 mu s, just apply the integrations. This would be r2 cube minus r1 cube by 3 r2 square minus r1 square, or this would be m by p. So all the three cases for uniform, this is for uniform p. Okay, and m by p will be equal to 1 by 2 mu s r1 plus r2. This is for uniform where, okay, p equal to c by r. So equation 5. So mu effective compared, so if flat has mu s, you can see that for any expression, see this over here, this is for a flat, half mu s r1 plus r2, and for a conical, okay, this value would be mu s half r1 by r1 plus r2 into mu s by sine alpha. Similarly, for uniform p, you have this 2 mu s by 3, and over here you have 2 mu s by 3 divided by sine alpha. So there is this effective factor of sine alpha dividing. So if flat is mu s, then conical is mu effective equal to mu s by sine alpha. Now sine alpha, as you know, is always greater than 0 and smaller than 1. So this would mean that mu effective will be greater than mu s. This implies that conical clutches are more effective for power transmission. Power transmission, as you can see by all of these formulas, is directly proportionate to the friction coefficient. Okay, so that's the case of conical clutches being more effective than flat bearings. Look at now the case of a sphere. So you have this sphere. So this is P, this is M, okay. This is total A at any generic distance, this is R, okay. So for a sphere you have a force P and moment M, okay, and this indents a flat bearing over a region A which is much smaller than capital R, which is the radius of the sphere. So indent means a sort of a pressing which is a somewhat of a permanent damage. Okay, so if you do not understand this word, see examples. Or let me put it, see real life examples. So you can just indent, Google the word indent and go to images and see what indent actually looks like. Okay. Okay. So now the indented area okay can be this area. Okay, this can be assumed or modeled as PR is equal to P naught 1 minus R square by A square 1 by 2. Okay, so what you have to do is again substitute this P into this expression. Okay, and then you should get a M by P. So M by P becomes 0 to A R into mu S P naught 1 minus R square by A square 2 pi R dr R square by A square 1 by 2 2 pi R dr. Okay, and this becomes equal to, so any relation which you can see between R and A. So if you substitute R is equal to A sine theta, it would not be very bad. Okay, how will you be able to do this? I think you have to draw an appropriate triangle. Okay, think of a triangle, think about this area. So once you do this substitution, one should have A by, let me just write the final expression. This should become 3 pi by 16 mu s into A. This is equation 6. Now let's take the example of a spherical ball bearing. So this was a sphere which was kept over a flat bearing. Okay, so this is a separate example. Now what we are seeing is this body 1 is a sphere. Okay, and you have this P, you have M, capital R. So this region is R, this is R plus dr clearly, this is ds. Okay, this angle is theta, this angle is d theta. Okay, and on this part you have this P acting at an angle of alpha, and clearly alpha is equal to pi by 2 minus theta, and the friction is acting mu s to P. Okay, so pull out equation 1 which was general. M by P is equal to R mu s P sine square theta okay, d theta p sine theta cos theta d theta. This is equation 7. So you have to do by the same method, okay? Just take this small strip ds and the area would be ds into dr, okay? Uh, okay. So in this case, for example, I mean the way to go about it is r will be equal to r sine theta, okay? ds will be equal to r d theta, and alpha is equal to pi by 2 minus theta. So once you substitute all of that in equation 1, you should get this for this case. Now let me draw another angle over here, okay? This is body 2, so this angle is beta, okay? So if you have a ball bearing in race, P is assumed to be either constant, okay, or P is equal to C by R. If you have sphere is pressed in elastic plate, okay, so this body 2 which is there is now elastic, it's not rigid, okay, and then you can assume that P is proportional to the normal indentation. So you do not have to know the result of this, because elasticity is perhaps something which you don't have to worry about now. In fact, even up till your 4th year, this is not something which you are expected to know, irrespective of your discipline. So take my word for it that if a sphere is pressed in an elastic plate too, okay, then you can assume that P is proportional to the normal indentation C, okay, and C, when I say, is actually this value, how much this has indented, okay, C. So C you can write as r cos theta minus, so once you write C is equal to r cos theta minus r cos beta, okay, you should be able to verify that the normal indentation is actually equal to this. Then just substitute it over there, and m by p should, for constant p, should come out to be r mu s 0 to beta sine squared theta d theta by 0 to beta sine theta cos theta d theta, mu s by r 2 beta minus sine 2 beta by 1 minus cos 2 beta. Now m by p again for p equal to c by r, make the substitution yet again. So that would mean that, see, r is equal to r sine theta, so this can be written as c by r sine theta. This would give us m by p is equal to mu s r tan beta by 2, and m by p for p proportional to c, which is the indentation. Actually this c is a constant, okay, this c is the indentation. Perhaps we should have a different symbol for it, okay, actually we should. So I'll just correct it to say I over here, okay, and I'll write this as I, okay, and this as I. Okay, so now P being proportional to the I is implies that P is equal to A into R cos theta minus cos beta. So M by P is equal to mu S R by 3 sine beta minus 3 beta cos beta minus sine cube beta cos cube beta minus 3 cos beta plus 2. So this is something you should verify all three equations. If there is, checks whether all this is clear. Okay, and it is needless to say that if you have a actual slip, so this was all for impending slip. For actual slip, replace mu k, replace mu s with mu k. Okay, so this is what can be said about spherical ball bearings. So these are very common in our applications, say of a bicycle. We have seen lots of them. Okay. So square threaded screws are very important machine elements. So they are so for example, you have power jacks, you have the lathe machine, which you must have worked on in your first year or will. Okay, on testing machine used to measure the tensile strength of solids or compressive. Okay, and even presses. Okay, so it's a very important machine element, and hence we are trying to study the frictional torque in this case, just trying to use the knowledge which we have over here. Now what do we have to do? Something similar to what we have just done. We want to compute the axial torque M needed to impend the motion of a bolt. So bolt is a kind of screw, but we might call it screw in this particular section, in a fixed nut. So by this time you have seen how nut and bolt go with each other against an axial thrust P. Okay, so we compute the axial torque M needed to impend the motion of a bolt in a fixed nut against an axial thrust P. So similar M by P is what we have to find. Okay, let me draw a diagram over here. So this is the bolt. Now let me just draw the threads on it. I'll draw it with a nice color. Okay. One thread, second thread, third thread. Okay. So these are the three threads I have drawn of the bolt, and then clearly you have this. Sorry, it should be black. You have this bolt, which according to the earlier section is the so-called body 2. The bolt is the body 1. So this is the nut. This is the bolt. You have a thrust P moment m, okay, and 2r is the so-called radius of this screw, okay, and this should come down like this, okay. This region is ds. This angle be called alpha. The pitch is L. Pitch is essentially the separation between the two threads, okay, or lead, sorry, L. So the length of the thread of the screw in contact with the nut be S1. So this is the total length of the thread of the screw in contact with nut. So you can take any point S, okay, inside this on the thread, and as long as it keeps on moving, and eventually when it comes out of the nut, then that measured distance is S1. So from 0 to S1. Mean radius is capital R, okay, and the lead is L. This is the separation between two threads, okay. Alpha is the so-called helix angle. It has been shown in the figure because the path taken by any point is actually helical, okay, that's why it's called the helix angle. So any point which you trace, say this particular point S, okay, the trajectory of it while it moves, okay, so if this is, if the nut is being raised, then this case this path, this point S would follow a helical path, hence you have this helix angle alpha, okay. Now you can actually have this L as L and then 2 pi r. So one complete rotation, okay, one complete rotation of this screw would mean that it has risen by a length L. So clearly there is a relationship between alpha. So tan alpha will be equal to L by 2 pi r, okay. This is because the helix axially advances by L for a circumferential distance of 2 pi r. So let me try to draw the free body diagram now of the bolt or the screw. So easy things first, P, M, okay, and say the threads are like this. So I'm just drawing two threads. So this is a small region ds, okay, and let me first draw this. I'll draw different ink. you have Ez, this angle becomes alpha. This is mu s p ds. Okay, and so you have p, you have mu s p, this angle is theta, this is q. Okay, so you have the FPD of the screw is shown over here. Okay, so the net exerts a distributed reaction force from one side of the thread of the screw. The nut exerts a distributed reaction force from one side of the thread of the screw. So in this case it is on this side of the thread. Okay, that's why it has been shown like this and like this. In a separate situation, whether it is rising or whether it is falling, you will have you may have the nut applying the force on the other face as well, but in this particular case it's the bottom faces. Okay, so you should please check which face in raise or fall. So if you have, say, a power jack, depending on what whether you want it to raise the tire or lift or bring it back to the ground. If it's a lathe machine or a vise, whether you want in which direction you want the lateral movement, sorry, the axial movement to be. Okay, so the nut exerts a distributed reaction force from one side of the thread. I have already talked about which side of the thread it is over here. Okay, now the width of thread is small. So this force, which force? This reaction force is modeled as a line load. At mean radius r. Okay, so sorry, this should be capital R. So the threads are on the periphery of the, I mean, they are somewhat extrusions on the periphery of the screw, and hence this force is modeled as a line load at mean radius r. Okay, just because the, say, if this is the axis and this is r and the threads are actually going out slightly over here, since this is too small, this distance, so it has been ignored. Okay, so what we have assumed is that the reaction force from the nut on the screw is acting as a line load at the mean radius r, just because this is too small. Okay, so for a small element ds, the normal force acting is pds. okay, and the frictional force for sliding is mu s pds. Okay, so that's easy. Now in this reaction force extends, so I'll use the path coordinate from 0 to S1. Okay, remember, I think I had just we had said that the length of the thread of the screw in contact with the nut be S1, so it's the total length. So just assume it's like a whole helical path. Say this enters over here and then enters over here in this nut and then keeps on rotating within this in a helical fashion, and if it finally emerges out. So S1 is that particular final coordinate, path coordinate. So that's why we say that this reaction force extends from 0 S equal to 0 to S equal to S1. So thread emerges from nut, in this one thread enters the nut. Okay, so P is clearly the normal force per unit length on thread. Okay, we have already shown that over here. Okay, so this makes an angle alpha with the axis of the screw. The axis of the nut is also the same. Similarly, the frictional force per unit length this is along the helix. In direction opposite to direction of impending slip. Okay, so we want to now write the force F on this small element ds. Okay, and this is located at a distance of r, small r, from the axis. This element ds is located at a distance of r from the axis. So we want to write df. Let's first write the normal. So the normal one has to be broken down into the E phi and Ez direction. So cos will be along the Ez direction, and sine minus sine alpha would be along the E phi direction. So let me do that. Minus sine alpha E phi plus cos alpha Ez, and then mu sp ds. Over here this angle is clearly alpha, so along the minus E phi direction we will have a cos alpha, or minus of cos alpha will be along the E phi direction, and then Ez direction would be minus of sine alpha. So this would be minus of cos alpha E phi minus of sin alpha Ez. Okay, so this is it. This is the force on a small element ds at length r from the axis, at the distance r from the axis. Now if you want to write the equations of equilibrium, the forces along the z direction, okay, will be added, and that should be equal to p, and similarly the moments also have to be added. So equations of equilibrium for axial force and axial moment. So 0 to S1 P cos alpha minus mu SP sin alpha ds and this would be r times of same. So it will be P sin alpha plus mu s P cos alpha ds. Okay. Okay, so you have to take up this and this for over here. Okay, so that's how you find the axial force and the axial moment. So just like last time, m by p would be equal to sin alpha plus mu s cos alpha minus mu s sin alpha. This would be r of tan alpha plus mu s by 1 minus mu s tan alpha. So what I have done is I have divided both the numerator and the denominator by cos alpha. So I get this, and tan theta is already equal to mu s. Okay, so this is something which we have already written over here, perhaps over here. So tan theta is equal to mu s. Okay, so now this quantity can be written as r of tan of alpha plus theta. Okay, so Q, if you see, is actually the resultant of this P and mu SP. Okay, so we want to now write its average value. Okay, so this is the average force per unit length on the thread. Average force per unit length on the thread. 0 to S1 P by cos theta ds divided by S1. So you take it, integrate this whole value over the path. And how can you find that Q? So just see that how Q and P are related. Where did it go? Okay. Q and P are related by a cos theta. So cos theta over here is equal to P by Q, or Q would be equal to P by cos theta. So that's why this is essentially Q. So you have done this whole integration and divided by S1, that gives us Q average. This particular quantity can be written as P sec of theta S1 cos alpha minus mu s sin alpha. Okay, so this has come from over here. Okay, this has come from over here. Now this is written as equal to P sec alpha plus theta divided by S1. So if the average force, I mean, remember in the belt we had the so-called maximum allowable tension. So here we can say that the threads will be sheared off if they are not strong enough to sustain Q average. Now if you can see that Q average can be reduced by increasing S1. Okay, you can see that it's somewhat inversely proportional, and this implies that by increasing the number of threads in contact with nut. So in the same region of, in the same so-called, say, L translation has to happen, you include more number of threads so that it keeps on passing through the helical path and the total distance traveled is S1, which is larger. Okay, so now the other thing can also be done. For example, the opposite torque minus M1 Ez. Ez, if you remember, is the axial direction. This is needed for impending motion in the direction of the axial thrust. P can be obtained from 1. So if you look over here, you can find the M1 for impending motion in the direction of the axial thrust. So for this case, just replace this m by minus m and mu s with minus mu s. Okay, replace m by minus m1 and mu s by minus mu s. This is because the direction of torque and the friction force in this case are opposite to those of previous. So you will have m1 by p is equal to r mu s minus tan alpha 1 plus mu s into tan alpha r tan of theta minus alpha. So we have a self-locking screw it does not advance under P in absence of M1. So it is self-locking if M1 is greater than 0. So unless you through a screwdriver or otherwise you apply a moment, it will not move up or down. Okay, the screw will not move up or down into the nut. So that's where this is. Okay, so tan of alpha is smaller than mu s. Okay, so that's where we can end our discussion on frictional torque for a square threaded screw.